So now we're going to introduce an extremely important but also extremely simple idea, which is called Bayes' rule. So in order to derive Bayes' rule, this is a very fast kind of proof, we just need to notice one thing. I'm going to start with the probability of A intersect B, and I'm going to rewrite it in two ways. So one way I can do it is I can say, hey, this is equal to the probability of A given B times the probability of B. Okay, that's a calculation we've seen before. But I could also equally as well swap the roles of A and B. And so I could choose to say instead that the probability of A intersect B is equal to the probability of B given A times the probability of A. Both of these are fully correct. They're just algebra. And so I can freely rearrange any pieces here. So I could, for example, divide through by probability of A given B, or divide through by probability of B, whatever I want to do. And there's one specific rearrangement that is extremely useful and important. This is Bayes' rule theorem. For any two events A and B, if I want to know the probability of B given A, I can calculate that if I know three other things. I need to know the probability of A given B, the probability of B, and then the probability of A. So if I know the probability of A given B, and I know the probability of B, and I know the probability of A, then I can calculate the probability of B given A. So I got this just by taking this side and I divided out the probability of A to isolate the probability of B given A. So this is a rule that we can use to calculate conditional probabilities from other conditional probabilities. And it was first given to us by this guy, Thomas Bayes. Thomas Bayes. So this rule is almost 300 years old now. And it really forms the heart of much of modern statistics and computer science. For now, let's just notice a little corollary here, another thing we can do with this. So if we additionally have the fact that, hey, there's some set of BIs which form a partition of some sample space that we care about, then we can write Bayes' rule in a slightly more detailed form. The probability of one of those specific B's happening, I'll call that one Bj, given that we know about A, is equal to the probability of A given that choice of B times the probability of that choice of B divided by the probability summed across all the possible choices of the BIs, the probability of A given BI times the probability of BI. So this denominator here is coming from P of A, the probability of A, applying the law of total probability to expand it out. So if we just kind of interpret each of these terms here, so this is what I know about the event B sub j. Over here, this first term, that's what I know about how A depends on the events B. And then over here, this is what I know about A after learning that B sub j is what happened. And then in this context, actually, this denominator here, it's just here to make sure that all the probabilities add up to 1. We often don't have to care about it too much. We just need to make sure we calculate it so that the probabilities all add up to 1, but we don't have to interpret it. So this gives us a recipe for saying, hey, if I know these conditionals or these conditionals, if I know all these conditionals, then I can swap the order. If I know the probability of A given B, I can compute the probability of B given A. This is extremely helpful in learning theory, broadly construed. And by learning theory, I'm including a lot of things. So learning theory is super useful in statistics, decision systems, artificial intelligence, natural language processing. We're using Bayes' rule all the time because Bayes' rule really is a mathematical expression of what it means to learn in the context of probabilistic reasoning. It tells me, hey, what does it tell me about B that A happened? And so we use it all the time. Now let's do a few examples with Bayes' rule. Okay, so let's work our first example using this expanded form of Bayes' rule here. So what I'm going to do is just remember what my different pieces are. So I need to calculate something of the form probability of B sub j given A, and what I'm going to assume I have access to is all the conditional probabilities in the other direction, probability of event A given B sub j, and probability of B sub j itself. And if I know those for all possible choices of j, I can calculate this sum on the bottom as well. So here's an example. Let's suppose that on any given day, there is a 15% chance of rain. Now, on rainy days, the probability that your friend Camilla is wearing a jacket is 90%. She's very likely to be wearing a jacket on a rainy day. Sometimes, though, she just wears a jacket because she likes to. So on non-rainy days, the probability that Camilla wears a jacket is 5%. So here's the thing. You see Camilla wearing a jacket. What's the probability that it's raining? What's the probability that it's raining if Camilla is wearing a jacket? So let's calculate. We want to know the probability of rain given jacket. The event I observed is that Camilla's wearing a jacket. I want to know the probability of the event that it's raining. And so Bayes' rule gives us a way to calculate this. So what I'm going to need the following items. I'm going to need the probability that Camilla wears a jacket given that it's raining. I'm going to need the probability that it's raining. That's the numerator of Bayes' rule. I need to draw a longer fraction here. It's the numerator of Bayes' rule. So what I start with is just this conditional, but in the opposite order. So I wanted probability of rain given jacket. Now I go to probability of jacket given rain. And I know probability of jacket given rain. That's my 90% here, the probability that Camilla is wearing a jacket on a rainy day. Okay, so now what I need to do is I need to get the denominator here. And to do that, I'm going to have one copy of the term that I've already written. So probability of jacket given rain times probability of rain plus, and now I need to consider all the other possible scenarios as well. And when I'm doing that consideration is here and here. So I need to ask myself what else could be happening other than rain, and the answer, of course, is no rain. So probability of jacket given no rain times the probability of no rain. So this is what I need to figure out. And fortunately, in my problem setup, I actually have everything I need in order to perform this calculation. So the probability of jacket given rain, well, we know that Camilla wears a jacket on 90% of rainy days. So I'm going to put a 9/10 here, and I need to multiply that by the probability of rain. There's a 15% chance that it's raining. So that's 3/20. Okay, next, I am going to consider the probability that it is raining and that Camilla's wearing a jacket. So this is the 910 times 320 again. So I got that from right here on the bottom. And then I need to combine this. So I need to add the probability that Camilla is wearing a jacket given that there's no rain, which we know to be 5%, 1 over 20, times the probability that it's not raining, which is 15%, or 3 over 20. And if we just do out all this arithmetic, we are going to get to 54 over 71. 54 over 71 is our answer, which is, in the ballpark of 3/4 or so. So the really big thing to notice here is that when we do this, we actually find something really important. I'm just going to move the 54 over 71 over here. We find something really important, which is that thinking that Camilla has worn a jacket that day changes our belief about whether or not it's raining. It makes us think that it's more likely that it's raining if we see Camilla wearing a jacket. So we started not knowing if it's raining, and we say, hey, it's rainy 15% of the time, so probably, it's not raining is my guess. But if we see Camilla wearing a jacket, suddenly our belief that it's raining should become much, much higher. Our belief that it's raining should now be more than half. And so learning something about the world, learning that Camilla's wearing a jacket actually changes our probability estimates about what's going on. So this is the paradigmatic application of Bayes' rule. We start with some belief, sometimes in statistical applications called the prior, about whether or not it's raining. And then after observing some data, specifically whether or not Camilla is wearing a jacket, we update our belief and obtain what we often call the posterior. So our posterior probability or posterior belief about whether or not it's raining. So let's do one more example where we apply Bayes' rule to learn how to update prior beliefs from data in order to form posterior beliefs. Many of us have become regrettably more aware of the problem of disease surveillance in the last 4 to 5 years. Let's see what Bayes' rule tells us about how to interpret the results of simple tests for diseases, especially when those diseases are relatively rare. So here's our problem setup for the example we'll do. Suppose that you're being screened for a rare disease that affects 1% of the population. So this 1% figure, we know that in general, this affects 1% of all people. This is often called the prevalence of that condition. Okay, so you go to visit your doctor. They administer a screening. They tell you that the screening test has a true positive rate of 90%. And a false positive rate of 10%. Then, regrettably, you find that you have tested positive in that test. And what you want to know, how likely is it that you in fact have this disease given that you've tested positive? So in order to calculate this, we are going to need to interpret some of the pieces that have been given here into probability statements, which we will then combine. So let's start with the prevalence. So the prevalence is that the probability of disease is equal to 1 over 100. If I didn't know anything about any tests, I just knew that 1% of the population was affected by this disease, then I would guess that maybe my chances of having it myself are 1 in 100. Okay, so this means that the probability of no disease before I learn anything about my test results is 99 over 100. That's 1 minus the probability of disease. Now, the next thing I need to do is I need to think about how the test works. So my doctor told me that the probability of a positive test, given that I have the disease, That's the true positive rate, and that is 90% or 9 over 10. On the other hand, the doctor also told me that the test has a chance to give me a positive result even when I do not have the disease, and that is 1/10 of the time. Okay, so what do we make of this? It's easy to kind of say, oh, true positive rate of 90%. It's easy to look at that and say, oh, if that's the case, then my probability of having this disease must be 90%, given that I tested positive. However, this really isn't how it works. I need to keep into account the prevalence. The prevalence is very important here, and the fact that the disease is rare also needs to factor into my considerations. How do I combine all of these ideas? The answer is Bayes' rule. So if I do my Bayes' rule calculation here, what's the probability of disease given a positive test? Bayes' rule gives us our formula for combining these pieces together. So in particular, it's the probability that I test positive, given that I have the disease, times the probability of having the disease, divided by the probability that I test positive, given that I have the disease, times the probability of disease, plus the probability that I test positive and have no disease, multiplied by the probability of having no disease. Okay, so here I now have everything I need to plug in all the numbers here. Up top, the probability of a positive test given the disease, that's the true positive rate, so that's 9 divided by 10. And the probability of having the disease, the base rate or prevalence, is 1 over 100. And then I divide by, I have another copy of that term, plus, okay, and now I have another term to consider, the probability of a false positive, so that's the probability of a positive test given that I do not have the disease, and that's going to be 1 over 10, times the probability of not having the disease, that's 1 minus the prevalence, which is 99 over 100. And if I multiply all this out, I'm going to get an answer of 9 over 108, which is roughly 8%. So here's the deal. I started with the prior belief that I had maybe odds of 1 in 100 of having this disease. And then I tested positive with a test that has a true positive rate of 90%. Now, what's happened is that my belief that I have the disease, it has not shot up from 1% to 90%. It's somewhere in between. It's 8% now. So much higher than 1%, but also much, much lower than 90%. So the effect of the test has been to make it more likely that I have the disease, but not all the way up here. I need to combine what I know about the true positive and false positive rates. I need to combine those with the prevalence in order to understand what evidence this test result gives me that I actually am affected. So our moral here is that when we're reasoning about testing for disease, especially rare ones, positive tests make it more likely that you have the disease, but if the prevalence is low, then your odds may still be good, depending on details of things like the true positive and false positive rates. So in order to properly interpret what we should believe, what evidence we have in light of medical results, we should be using Bayes' rule to do it.